All right, today we're jumping into a really cool paper from 1990 that honestly changed how we see the world. I mean, literally, at the atomic level. It all boils down to this one kind of simple but really profound problem. How do you clean up a picture when your subject is, well, individual atoms? So picture this. It's the late 1980s, and science has just pulled off something incredible. We can actually take pictures of atoms. I mean, wow. But there was a massive catch. The pictures, they weren't telling the whole truth. They were a bit of a lie. So the big question became, how do you find the real, honest-to-goodness signal when your image is full of static?
Okay, so first up, imaging at the atomic scale. Before we really get into the weeds of the problem, you've got to appreciate just how wild the technology that made this all possible was. I mean, we're talking about stuff that was pure science fiction just a little while before. These pictures were coming from these amazing new tools, like scanning tunneling microscopes. They created what are called near-field images, which for the very first time let scientists see individual atoms. We're talking about resolving details smaller than 2 angstroms. It was, and I'm not exaggerating, a total game changer for material science. And what everyone wanted to do was pretty simple, right? They wanted to use this incredible new power to see the pure, perfect, repeating patterns of atoms inside a crystal. You know, that beautiful, orderly grid that makes up so many materials. But, as it always goes, the real world turned out to be a whole lot messier. Which brings us to our next part. A picture full of static. Yeah, that dream of a perfect crystal image, it slammed right into a messy reality. The pictures coming out of these incredibly expensive, high-tech microscopes were just, well, they were full of noise. So instead of getting that clean, perfect crystal grid, the images were contaminated. It could be anything, really. The way the sample was prepped, tiny little instabilities in the microscope, all of this stuff would basically create a layer of visual static that just smeared itself all over the real atomic pattern underneath. Now, the paper has a technical name for this, of course. It's called aperiodic background. Aperiodic just means it doesn't repeat in a pattern. So what you've got is this beautiful repeating signal from the crystal totally buried under this random, non-repeating layer of junk. It's kind of like trying to look at a detailed photograph through a dirty, smudged window. So, how did scientists deal with this mess? Well, the paper puts it perfectly. They were using ad hoc recipes. Think about that. Recipes. This wasn't rigorous science at all. It was more like a scrapbook of little tricks and best guesses, and every lab had its own secret sauce. It was basically an art form, not a scientific method. And that right there gets to the heart of the problem. The old way? It was basically just guesswork. You'd kind of just assume the background noise was 0, which of course just created a whole new set of errors. The new idea this paper brought to the table was revolutionary. It said, let's stop guessing. Let's use a principled approach, one that's actually based on the physics and probability of the situation.
And that leads us right into Section 3, the Bayesian solution. This is it. This is the big breakthrough. The author of the paper proposed using a really powerful statistical tool to crack this nut, something called Bayesian inference.
Now, this is the core idea, and it's so clever. Instead of just trying to, digitally erase the noise, the Bayesian approach is all about making an intelligent, educated guess. It asks a much smarter question. Okay, given this messy picture we're looking at and everything we already know about what the noise should look like, what is the most probable, true, clean picture that's hiding underneath?
So how does this actually work? Well, it's a 4-step process, and it's way smarter than just hitting delete on the noise. First, you analyze the messy image, right? Recognizing it's a mix of the true signal and all that background junk. Then, you use what you already know about the physics to estimate what that noise probably looks like. But here's where the magic really happens. Based on that noise model, you calculate the most probable true crystal pattern that would create the messy image you see. And once you have that, boom, you can subtract that probable noise, and what's left is the clean, beautiful underlying structure. It's so elegant.
The whole point, as the paper says, was to systematically minimize noise. And this wasn't just about making the whole picture look better. This new method was an absolute superstar in the faintest parts of the image.
The places where the real signal was super weak and the noise was screamingly loud. And why does that matter? Because that's exactly where all the most interesting science was hiding. The tiny defects, the boundaries in the crystal, all the good stuff. Okay, last section, from recipe to rigor. So what was the big picture impact of all this? It was nothing short of a fundamental shift. It took the whole field from using these folksy, qualitative recipes to doing quantitative, rigorous science. And let's be clear, this was never, ever just about getting prettier pictures. It was about being able to pull out far more accurate, more reliable scientific data from those images. By cleaning them up the right way, scientists could finally start to properly study what the paper calls the fine structure of materials, all those tiny, absolutely critical details about defects and boundaries.
I mean, this one single technique unlocked a whole new universe of research. Suddenly, scientists could accurately study things like nanometer-sized diamonds found in meteorites. They could investigate these weird, super complex structures called quasi-crystals. They could even tell the difference between crystals with really subtle phase relationships. It's amazing. One mathematical idea just blew the doors open for countless new scientific adventures.
And just think about it. This massive paradigm shift. It all started with a single paper published back in 1990. It's just such a powerful reminder of how one brilliant idea can give us the tools that go on to shape entire fields of science for decades. So when you boil it all down, this story isn't really just about cleaning up a picture. It's about a much deeper shift in thinking. It's about using the power of probability to find a clear signal that's buried in a whole lot of noise. And that leaves us with a really fascinating question to chew on, doesn't it? If we can do this for pictures of atoms, what other kinds of noise, in our data, in our world, even in our own thinking, could we learn to filter out, to see what's really there?